Hello, my name is Faílde, and together with my colleague and mentor Baldomir, we are currently carrying out a project for studying the thermoelectric and magnetic properties of topological materials, especially topological insulators. We are part of the Technological Research Institute of the University of Santiago de Compostela in Spain. Attending to our work, the present study entitled Orbital Dynamics in Two-Dimensional Topological and Chern Insulators, which has been published in NewJournalofPhysics, focuses in one of the principal magnitudes for the topological materials, which is the very curvature, for generalizing previous studies in the field into the proper relativistic context of these materials. This is done through a perturbative formalism, which starts directly from the Dirac-Hamiltonian and goes further in the physical interpretation of the problem by considering the very curvature as a dynamical magnitude. Generally speaking, within Gauss theories, the curvatures are invariant under a group of transformations, which helps enormously to represent it as physical observations. Examples of these are the electromagnetic field for the U1 group, which transforms the potential, leaving a degree of freedom, or its generalization of the Jamnis fields for the SUN non-abelian unitary groups. The important thing is that the curvatures can be represented as fields for Lie groups, and this allows considering the very curvature within the U1 group as a kind of magnetic field in the momentum space. Additionally, given that these groups are topologically non-trivial, this allows to the very curvature by classifying the topology of the materials to the Chern polynomials. Coming back to the Dirac-Hamiltonian, on each Dirac band, we can define the very curvature from the rotational of a vector potential, namely the very potential. And given that, it's even logical to ask that a positive very curvature will be enhanced by a positive magnetic field parallel to it, or reduce it if we take the magnetic field as antiparallel. This behavior is obtained in our work through analytical expressions which are demonstrated to not alter the topological invariant Chern number of the system. And in a schematical framework, we can imagine the electrons orbiting with a definite radius, velocity, orbital magnetic moment, energy, density of the states due to the non-zero very curvature. So, introducing a magnetic field, we will have a redefinition of these quantities based on the change of the field felt by these relativistic electrons. All these elements, together with others such as the quantum metric, the free energy, the orbital magnetization and orbital susceptibility, are given in analytical expressions to complete this study of the orbital dynamics in non-zero very curvature systems. The present results are suitable to be applied to any non-zero very curvature system to introduce new interactions or to study new efficient head electricity routes in topological materials. That said, we take this opportunity to invite you to read our work and contact us if you find it of interest. And finally, thanks for your attention.